Hello and welcome to this presentation with the topic How does creativity relate to engineering, which belongs to Unit 1 of the Tycoon Learning content. The purpose of this presentation is for you to acquire insights in the definition of creativity, the profession of engineering, the engineering design process, the stages of creativity, obstacles of creativity in engineering education, and how to implement and improve creativity. In the following slides, we collected different definitions of creativity in engineering education so that you can develop a better understanding. According to Plugger et al., creativity is perceived to be a dynamic process rather than a solid product. Creativity is the interaction among aptitude, process, and environment by which an individual or group produces a perceptible product that is both novel and useful as defined within a social context. Kraepelin, Huffman, and Kraepelin argue that creativity is strictly related to the act of divergent thinking, which is defined as the ability of establishing unusual connections and being able to reach surprising results. Hurdle and Tarkovsky write that to be able to achieve such a target, one needs to have openness, willingness to take a risk, ambiguity, and tolerance of uncertainty. Correspondingly, Kraepelin lists key traits of creativity as critical aptitude and optimism, knowledgeability, acceptance of fantasy, and adventureness, flexibility, self-criticism, and lastly autonomy and courage. Now we will take a closer look at the profession of engineering. The profession of engineering demands many skills. Engineers should recognize, certify, and solve problems which exist in our society. Once they recognize a problem, they should innovate and find better solutions to those. Most important for the profession of engineering is to demonstrate original, critical thinking, creativeness, and innovativeness. Engineers need a creative and curious mind to meet the progressing goal of the engineering profession and to develop new products and to improve existing ones in order to benefit society. Now we will try to answer how creativity is related to engineering. Creativity and engineering are intertwined concepts. Creativity, engineering, and innovation are concepts that cover a certain axis. However, Kraepelin states that in general evaluation of engineering programs, there is a disconnect between creativity, innovation, and engineering. Hornstein states that if more than one solution exists, and if deciding upon suitable path demands, making choices, performing tests, iterating, and evaluating, then the activity is most certainly design. Design can include analysis, but it also must involve at least one of these latter elements. Let's have a look at the 4 phases of creativity. This conceptual framework is defined by Rhodes, which links engineering and creativity. It contains the items, person, product, process, press, and an additional 5th item, phases. It's a useful framework derived by Rhodes that provides a deep understanding for the who, what, when, where, and how of creativity in engineering. There are many models of the engineering design process which are basically based on taking an idea, adjusting it, and providing certain details for production. One of the most highly developed and determined models is the German model by Paul and Beth. This model contains 4 phases. First, clarification of the task. Second, conceptual design. Third, embodiment design. And lastly, detailed design. At the beginning, a need must occur that has to be satisfied with the accomplishment of the process. During the process, you can assess the individual phases and their outcome. You can go back to previous phases and make further changes. This is why it's more of a cycle and you can always improve the result. Now we will take a closer look at each phase. The first phase, clarification of the task, starts by specifying the requirements of the new design, product, or process. This includes market research or customer surveys. The accomplishment of those activities should result in well-defined requirements. The requirements should reflect both the demands and wishes of the customer. The resulting requirements specification is the document from which the solution must be generated. The second phase, conceptual design, establishes a solution concept to satisfy the demands and wishes. The creative activity of conceptual design involves the decomposition of the problem into several subfunctions. Additionally, it involves creating solution principles for those subfunctions and combining them into suitable conceptual options. These solutions are evaluated under consideration of the requirements, specification, and the best and most suitable concept it is defined. In this process, creativity and creative thinking are vital, and its application is important to the overall design process. The third phase, embodiment design, involves the assignment of the technical principle from the conceptual solution into a final form. The final form should enable the production of the final layout of the selected design. This typically contains the spatial arrangement, component form, and lastly the production process of the solution. The last phase, detailed design, is an evolvement to the embodiment phase to reach the state that the product can be manufactured. This usually implies tasks like finalizing form and dimensions, producing in-depth design, and manufacturing drawings. Afterwards, the product can be manufactured. There are different techniques and methods for each phase of the process, which you can find in our toolbox on the website. Another way of showing the relation between creativity and engineering are the stages of creativity. In total, there are 5 stages, which we now take a closer look at. The first level consists of expressive creativity, which is the ability to generate a unique idea with no fear about its quality. The second level is specified as technical creativity. This includes the proficiency to create products with excellent skills but with little spontaneity. The third level is defined as inventive creativity, which is the ability to develop a new use out of something old and to see all things in an ingenious new way. The fourth level consists of innovative creativity. This is the ability to establish foundational principles and formulate innovative ideas. The fifth level is specified as emergent creativity, which is the ability to incorporate the most abstract, additional assumptions or principles underlying a wide knowledge. Engineers should try to reach the creativity level of innovative creativity, which is a suitable level for the profession of engineering where scientific principles, new ideas, and findings are applied to establish new products and services. Now we will have a closer look at possible obstacles of creativity. There are several obstacles that undermine creativity in engineering education institutions and programs. James Sullivan divides blocks regarding creativity into 4 categories in his book entitled Conceptual Blockbusting. The categories are called perceptual blocks, emotional blocks, cultural and environmental blocks, and intellectual and expressive blocks. For further obstacles that can cause creativity to be ignored in higher education institutions. These are, for example, engineering degree programs place too much emphasis on narrow specialization. These programs have an excessive focus on acquisition of factual knowledge. The academic personnel are not equipped with a detailed understanding of creativity, and students don't know how to properly evaluate and select creative ideas. And lastly, students avoid the design process rather than seek radical innovation. According to Hurdle and Tarkovsky, the main obstacles are teachers' prior experiences, teacher-dominated convergent teaching approaches, pressure to stick to the plan, unexpected student ideas are disruptive, wrong beliefs, behaviors, and assumptions about students, scripted curricula teaching to the test, and increased use of external mentored fact-based tests is the last main factor that undermines creativity in engineering programs. Further obstacles in higher education engineering programs can be that standardization or over-specialization may undermine creativity. According to Crowley, over-specialization leads to the loss of key skills and abilities such as design, creative problem solving, and abstract thinking. Hurdle and Tarkovsky state that creative students need creative teachers. Another obstacle against creativity in engineering derived by Crowley is the lack of knowledge problem. Atwood and Press argue that the current engineering curricula is far behind the ideal of appropriately teaching and rewarding creativity. The graph you can see here display actions that discourage creativity. Most of us are aware of a few of those actions. For example, we all know that early criticism will make the creative person more cautious, defensive, and or more speculative. Criticism is one action which is also displayed in the graph. Other actions are, for example, disagreeing, arguing, being impatient, giving no feedback, and only pounding out applause. This section brings together the recommendations of how to promote creativity in engineering education. A possible solution to the narrow specialization of engineering programs is listed in Sternberg and Crowley as follows. First, students have to develop the habit of applying creativity. Second, students must have the opportunity to engage in creativity. Third, students should be provided with positive encouragement as they engage in tasks requiring creativity. And lastly, the curriculum must be designed to reward students when they apply forms of creative thinking. The graph you can see here is the contrasting graph to the one we have seen before. This graph displays actions that encourage creativity. A few examples of encouraging activities are to evaluate the learning in mistakes, to be optimistic, to listen, and give early support. Now we have reached the end of the presentation. We hope you could get some insight in how creativity relates to engineering. The presentation was done by Yanezheska Bia from Hochschule der Medien and Ekremulus from Ege University. The voiceover was done by Deniz Alagöz from Ege University.